Welcome back, students. In this video segment, we will cover section 12.2, vectors. Vectors are a very important part of mathematical physics, which means a very important part for the mathematics of the sciences. So I thought I'd give you a little bit of a description of examples of vectors versus things that are not vectors, just to get things started. It's kind of a long section, so I think I'll give you a little bit of an introduction to what these things are before we dig into the algebra and geometry of these things. So suppose that, for an example, suppose that I'm on the 605 freeway in my car. So suppose I'm on the 605 freeway in the car. So here's the 605 freeway. Okay. And don't laugh when I'm going to try to draw a car. No, you could laugh. I'm never going to hear it. So I'm not an artist. You're going to discover that real soon in this course. Here's my car. We're looking straight down onto the 605 freeway from a bird's eye view. Okay. So here's the cabin of my car. And here's either the front or rear windshield. Here is also either the front or rear windshield. I'm not going to say which. And suppose that I'm given one other thing besides the fact that I'm on the 605 freeway. I'm moving 60 miles per hour. 60 miles per hour. Okay. So what I have here is an example of something that is not a vector. What I'm given here is called a scalar. A scalar is, in this case, is the speed of my car. Now, scalars represent much more than just the speed of things. But in this case, my speed is an example of what's called a scalar. Now, I'd like you to think about something that's missing here in terms of, suppose I was in my car and somebody wanted to know where I was headed and how fast. What's missing? They call me on the cell phone. They got me on the cell phone, and I say, I'm going 60 miles per hour. What's missing? You probably got it, but let's take a look at our next example. Okay. Now we're back on the 605 freeway. Okay, so we're back on the 605 freeway. And this is what our situation is. A little bit different. I'm still given that I'm going 60 miles per hour, so someone's called me on my cell phone, and I've answered while I'm on the freeway, and I say I'm going 60 miles per hour, and I'm headed toward, let's say I just got on the freeway off Cerritos College, supposing we're able to go back to Cerritos College someday. I think we will. And I'm traveling home. I live in Long Beach. So the complete description would be, I'm on the 605 freeway going 60 miles per hour headed home, or I'm on the 605 freeway going 60 miles per hour headed south. That description is an example of a vector. This is an example of a vector. And this vector is called, this particular vector is called velocity. Now you might think, it's the same thing as that scalar. We'll look back at the scalar. The scalar in red is speed. The velocity is not speed. Velocity is not speed. If you've had physics, you know that. But a lot of people haven't had physics yet. Velocity and speed are not the same thing. Okay, the speed was 60 miles per hour. The vector is 60 miles per hour headed south. Okay, so the vector, another way to describe this vector would be 60 miles per hour south. Okay, So the vector includes the 60 miles per hour. It also includes direction. That's the bottom line. Vectors include both amount or magnitude and direction. Vectors include two aspects, amount or magnitude. Magnitude is the amount of something. Magnitude. You only have a positive amount of something, and includes also something called a direction. So vectors include magnitude and direction. Now go back to our scalar. The scalar will only include magnitude, amount of speed, magnitude, 60 miles an hour as opposed to 20 miles an hour or 30 miles an hour or whatever. Okay. Now when we deal with vectors in, let's say, physics, well, we don't need to draw little cars with their headlights on. That's not real practical. So what we do is we simplify this. What we do, instead of drawing a little car with the headlights, is we simply draw an arrow. We draw an arrow. But not just any old arrow. The direction of the arrow gives the direction we're moving. And if you were to measure the length of the arrow, the length of the arrow would give us our speed. The length of the arrow would be 60. Okay, the length of the arrow would be 60. And the direction is south. The length is 60. The direction is pointing south. So what's the bottom line in all this? The bottom line in all this is that vectors are the simplest way to describe a vector. It's an arrow. An arrow. It's simply an arrow. So supposing I have a car behind me going 20 miles per hour south. So what I would draw is a little arrow of length, let's say 1/3 of the length of my 60 mile per hour arrow, and this car then would be represented, or the velocity of this car would be represented by the arrow pointing south, and the length of the arrow would be 20. So this would be a way of describing the vector 20 miles per hour south, magnitude 20, direction south. So vectors are, the verbal description, vectors are quantities with both magnitude or direction. Geometrically, they're arrows. That's all that they are arrows in space. That's all that vectors are. Now, there's something missing, perhaps, from the description of these velocity vectors. Back to the cell phone example. I'm in my car on the cell phone. Somebody calls me and says, "What's going on?" And I say, "I'm going 60 miles an hour headed south." Now, what's missing from that description, from the point of view of the person calling me, is, well, where are you? Where are you at the moment? You're going 60 miles per hour south. Are you in Pico Rivera? Are you getting ready to get off the 605 freeway and transition onto Bellflower? So what these vectors don't include, what vectors don't include are location. Vectors are not defined by their location in space. Now this is very, very important. Vectors are arrows in space. So a vector that represents me on the 605 freeway going 60 miles per hour south could be represented by this arrow, this one, this one, this one. There are an infinite number of arrows, vectors, that can be used to describe 60 miles per hour south. Okay, so vectors don't have position, location in space as part of their definition. Okay, some vectors, special vectors, can have these added things, these things added to them, in which case we get special other kinds of vectors, but there are vectors that have some sort of location associated with them. We'll talk about those in about 3 to 5 minutes from now or so. But right now, vectors have the definition of a vector has nothing to do with location. Okay, so what are other examples of vectors? Well, if I were to jump out of an airplane, if I were to just jump out of an airplane, that's a pretty gruesome example, but suppose I jump out of an airplane. If I jump out of an airplane, or let's say, even better, I jump out of a helicopter that's hovering above, so I'm not moving to the right or left or north or south or whatever. I'm just hovering, and then I jump out without a parachute on. I'm going to begin to travel toward the Earth due to the force due to gravity. Gravity is going to pull me downward. As long as I'm pretty close to the surface of the Earth, and helicopters can only stay pretty close to the surface of the Earth, my acceleration due to gravity is going to be the same, no matter where I am after I've jumped out of the helicopter. Okay, so here's the Earth. Here's the Earth. If you've had physics, this is probably painfully slow for you, but bear with me. This course gets extremely involved. This is one of the most difficult calculus courses. So if you're finding this very easy, enjoy it while it lasts. Okay, so it gets pretty rough. Okay, onward. Anyways, so here's my location above the Earth. I can draw a vector to represent the acceleration due to gravity. Here it is. The acceleration due to gravity. The Earth is attempting to pull me toward the center of it. The Earth exerts a gravitational force that pulls me toward its center. And the interesting thing is I also exert a very small force on the Earth, attempting to get the Earth to come toward my center of gravity. But that's negligible, since the Earth is much more massive than I. The force due to gravity much exceeds the force that I exert on the Earth. We all have our own personal gravitational force based on our mass, in fact, directly proportional to what our mass is. So anyways, enough of that. The Earth is exerting a force on me, and that force will result in gravity. The Earth is pulling me toward its center with an acceleration of 32 feet per second every second. That means 32 feet per square second. That means when I jump out of the helicopter, 1 second later, I will be moving 32 feet per second in velocity. My velocity will be 32 feet per second. 2 seconds later, I will be moving approximately 64 feet per second, etc., etc. So I will gain velocity at a rate of 32 feet per second every second. 32 feet per second, or 32 feet per square second acceleration. So that description alone, without the arrow, is a scalar. With the arrow, I get 32 feet per square second acceleration downward. Okay, downward. And that gives us our vector. The vector could be described as 32 feet per square second downward. Okay. All right. So those are two examples of vectors. There are many, many other examples of vectors. Vectors are at the center of mathematical physics. I mentioned that a few minutes ago, or 10 minutes ago or so. There are some special vectors. There are a lot of special vectors, but there are a couple of special vectors for our course. Special vectors. Remember, the definition of a vector does not include location. But these two special kinds of special vectors also include in their definition location. There's something called a position vector. Position vector. If I draw an arrow if I draw an arrow, let's say in 2 space. All of this generalizes to 3 space, but let's just keep us in R2 for right now. So let's suppose I draw a vector this way. A vector drawn this way. I start at the origin, I move 3 units to the right, and then move 4 units up. There's a vector. This is a vector. What is a vector? It's an arrow. Vectors are arrows. That's what a vector is. A vector geometrically is an arrow. It's not a location. But if I draw a vector with the tail end of the vector at the origin, that's called a position vector. It is a vector with the tail drawn at the origin, or the origin in 3 space 0, 0, 0. Okay. Okay. So there's another kind of vector. Suppose I'm in R2 and my start position is, let's say, at A, and my ending position, let's say, is at B. This is my end position. If I draw an arrow from A to B, it's a vector. Vectors are arrows, but it includes something more than what a vector has. It includes a starting point and an ending point. It includes a position in space. It's a really thick arrow, I just realized. This is called a displacement vector. This is called a displacement vector. A displacement vector has a starting point A, some starting point A, and some ending point B. So these 2 vectors are special vectors. They do include position in their definition. But vectors generally, I know I'm repeating this, but this is very important. I'm repeating it only because students tend to not really understand that the definition of a vector is independent of location. The definition of a vector doesn't have anything in it to do with location, but there are a couple kind of special vectors that do. Okay. So, what is a vector? Vectors are arrows in space. That's the definition of a vector. We need a lot more with vectors. Ultimately, we need an algebra of vectors, which we're going to basically invent as we go along. Not for the first time, but we're going to invent as we go along. And there's a calculus of vectors. Vectors play a central role in the mathematics of motion, which is calculus, okay? Another way to think about vectors is that it's more generally any quantity, not just any quantity, but any quantity having 2 things, having both magnitude, size, which means size or amount, magnitude, which is the length of the arrow, and direction. Okay, so any quantity having both magnitude and direction. Those are vectors. Okay, but not necessarily position. Okay, so let me draw a vector. Here's a vector. Okay, I mentioned a word without defining it. I mentioned the starting point of this vector. I called it the tail of the vector. That's generally what we call the tail of the vector. The other part of the vector, where the little arrowhead is called the tip of the vector. Okay. How do we write vectors algebraically? What do we use to designate a vector algebraically? We use letters just like we do with scalars. A scalar is just a real number. Remember the scalars I used to describe my going 60 miles per hour. 60 miles per hour, that's a scalar. Without direction, it's a scalar. It's a real number. And we use letters to designate scalars. We use letters to designate vectors, but there's a difference. Vectors are designated in bold print. Vectors are typed. Vectors are typed in boldface. Boldface. Okay, vectors are typed in boldface. So if this is the vector u, we would designate this vector in boldface type. This is the vector u, the vector u. Now that's not practical. It's not practical to write in boldface, for one thing. My boldface looks really ugly. Here, it still looks the same. We need to lighten it up a little bit here. Here. Oops. Here, it still looks the same. So you see there's a problem with writing vectors. So when we write vectors, which is going to be what you do all the time, you write vectors using the scalar notation, just the regular old u, and you put a little arrow over it. Now I want to give you a bold, not a bold, but a warning. Warning. This is very important. This is a very large source of loss of points on the first test generally in a Calc 3 class, Calculus 3 class. You must use arrows to designate vectors. Vectors. You must. It's not an option. If you just write u on a test or an exam or whatever, I guess tests are exams, that is going to be interpreted as a scalar. And if you want it to represent a vector, you're going to lose points for it. This is very important. If you want to designate a vector in writing, you draw a little arrow above it. Okay, you must. It's not optional. I know I'm repeating this, but it's kind of important. Well, it's more than kind of important. It's extremely important. It's critical. Okay. So, just to bring up the concept of a displacement vector, a very special vector, a displacement vector. Displacement vector. Suppose I start at a point A and I end at a point B, and I'll use green to designate this displacement vector. So the vector, the arrow from A to B, and let's say I want to use the letter V to designate this arrow. The displacement vector would be V equals AB. Arrow. V with an arrow is AB. Okay. Okay. Now, what we're going to do is we're going to basically invent or discuss the algebra of vectors. Now, this is probably one of the only places in the course where it's better if you have had no exposure to vectors, because the tendency of students who have had physics is to ignore the next 20 minutes of lecture, and it's disastrous for your first exam. This is very, very important that you do something. If you've had physics before, or if you studied vectors before, abandon your knowledge of vectors temporarily and accept only what I present to you. You got to do this, okay? If you haven't studied vectors before, this doesn't apply to you. You just start taking this in as we go. Okay, we are going to invent an algebra for vectors. An algebra meaning addition, subtraction, multiplication, division, that kind of stuff. And it's not obvious. It's not at all obvious. Some things seem obvious, but some things are not. For example, there is vector addition. There is vector subtraction. There are three kinds of vector multiplication for us. There are other types of vector, many other types of vector multiplication. There's no such thing as division of two vectors. There's no such thing as division of two vectors for us. Okay, so there's more to this vector algebra than just assuming that the properties of algebra that we know for scalars translate into the properties of vectors. They do not. They do not. Okay, so let's start fresh. Let's start fresh. All right. Well, we have to go one step before addition, subtraction, the operations, and multiplication. We have to go one step before that. What do I mean? What do you need in an algebra or arithmetic before you even start with the concept of addition, subtraction, and multiplication, division, or whatever? You need the concept of equality. What does the equal sign mean? What does it mean for one vector to equal another vector? So we have to start from the very beginning. So what does it mean for two vectors to be equal? Equality of vectors. Well, what is a vector? I don't mean a displacement vector or position vector. I mean what generally is a vector. It's an arrow. So how do you think we're going to describe two vectors being equal? What does it mean for two arrows to be equal to each other? Well, here's the vector u, an arrow in space. It seems reasonable that for this vector u to equal some other vector v, then the two parts of the definition of the vector should be satisfied, should be equal. Two vectors are equal if they have what? The same what? Well, vectors have two things. They have magnitude and direction. So two vectors are equal if they have the same magnitude and the same direction. U and V are equal if they have the same magnitude and the same direction. Two vectors are equal if they have the same magnitude and the same direction. So the way I've drawn these two vectors is that u equals v. So true or false? The two vectors that I'm going to describe now are equal. True or false? The two vectors I'm about to describe are equal. The first vector on the 605 traveling south at Alondra, and I'm at Alondra, there's the first vector. Traveling south at 60 miles per hour, but I'm located at Alondra. The other vector is traveling on the 605, traveling south at South Street. Are those two vectors equal? True or false? Yes. Do they have the same magnitude? Yes, 60 miles per hour. Do they have both the same direction? Yes, 60 miles per hour. South. So let me add the third vector. Going south, 60 miles per hour on the 710 at the 91 freeway. Going south, again, 60 miles per hour, location 710 at the 91 freeway. Yes, all three of those vectors are the same. All three vectors have a magnitude of 60 and a direction south. So what's missing from the definition of a vector is location. So two vectors are equal if they have the same magnitude and the same direction. Okay, so now we're going to get into it. For those of you who had physics, I want you to abandon your knowledge of vectors just temporarily, and just start as though You know nothing about vectors. We need an algebra of vectors. We've got a good start. We have a definition of equality. Okay. We need addition. We need subtraction. We need multiplication. Division. There is no division. There are 3 kinds of multiplication. And they all mean different things physically. By the way, all of this discussion of vectors, all of the ideas that correspond with vectors and their definitions and everything else, algebraic definitions and stuff, they were devised, they were discovered in order to make the study of physics doable, easier. Vectors do amazing things. You might, as we go through this, you're probably going to be, especially if you haven't studied vectors before, you're going to find this discussion very abstract, and you may ask the question, why do we need these things? They are at the heart of making the mathematical physics doable for us. Okay, so once we have the algebra of vectors, we need to talk about a calculus of vectors, not in this section. Calculus of vectors. What does a calculus of vectors mean? It means limits involving vectors, derivatives, integrals. They all have meaning. They all have meaning. Okay, so let's approach these things. Let's start at basically the beginning. Well, we have equality. Now, let's talk about addition. Our definitions have to be, at this moment, they have to be geometric as opposed to algebraic. They have to be geometric. Why can't they be algebraic? Because we're talking about geometric objects. What is geometrically a vector? It's an arrow. It's not a number, it's an arrow. So how do we add 2 arrows up? That's a really deep question. Okay. We would like to define addition of vectors to make sense in physics. So specifically, suppose we start at some point A in 3 space, and we move to some point B in 3 space. You can think about it as we're in a boat or a ship at sea if you want. And then once we get to B, we turn and then head toward C. So we move from A to B, we turn when we're at B and head toward C. We can designate as a displacement vector the vector whose tail is at A and whose tip is at B. We can use as a second displacement vector a vector that has its tail at B and its tip at C. So we would like to be able to add these vectors up. So I'm going to call the displacement vector from A to B U, the vector U. Don't forget the arrows again. That'll be expensive on an exam. Don't forget arrows to designate vectors. Okay, so the vector V is a displacement vector from B to C. We would like the sum of these 2 vectors to give another displacement vector. We want U plus V to give a displacement vector. To give a displacement vector. Let's not say a displacement vector. To give the displacement vector. The displacement vector from A to C. We would like the vector u plus v to give the displacement vector from A to C. So how do I define the what is the definition of vector addition? You're looking at it. You're looking at it. Is it enough? No, no, no. We have to devise a symbolic algebra, not just a geometry for these definitions. So it's not enough, but it's a hell of a good start. Okay. This way of describing u plus v is called the triangle law. This is called the triangle law. The triangle law gives us a way of visualizing vector addition. Okay, that's all we have for right now is this definition, and it's going to work pretty well. So here's an example. Here's an example. True or false? True or false? U plus v equals v plus u. Now, if you've never had vectors before, if you've never studied vectors before, and you answer right away true, you're probably making a mental mistake. If you're thinking this is true because of algebra, because x plus y equals y plus x for scalars, and if you're thinking that generalizes to this is dangerous. This can be very, very costly to think about it this way. So if you haven't had vectors before and you're thinking, I don't know, we're talking about vector addition in terms of a triangle law, I don't know. So let's check it out using the triangle law. That's all we have right now. So again, here's A. Oops, that's not A. It looks like something else here. Okay. Here's A. Here's B. Here's C. Let's look at the definition of the left-hand side of this equation, u plus v. We'll do that using green vectors. U, v, and I'll write the result. The result of adding vectors, by the way, is called the resultant. Resultant. The result, I should have brought that up. So here, some vocabulary. Wait, yeah, that's the ugliest squiggly arrow I've ever written. Maybe the second ugliest squiggly arrow. I'm trying to avoid using arrows to point to things because arrows are vectors. So anyway, okay, whatever. This little arrow here is called a resultant. Okay. So the sum of two vectors, the result is called a resultant. So here's u and here's v. Let me draw the resultant vector in the same green. So there's u plus v. Now let's consider v plus u. We're going to change colors here. Let's consider in red v plus u. How do we add two vectors? Well, we start at A, and we start with v as a displacement. So the vector, draw the vector v, that little green vector to the right with vector v. Here's the vector v I've just translated over. How can I do that? Because vectors have nothing, the definition of a vector doesn't have anything to do with location. So there's v. And if I'm at the tip of v now and I turn towards c, that displacement vector will be u. So if I draw the resultant vector from the tail of v to the tail of v to the tip of u, There's the vector v. Oh, yeah. There's the vector v plus u. And they kind of are the same vector. The red vector v plus u is equal to the green vector u plus v. So it looks like, geometrically, it looks like we have a true statement. It looks like we have the statement that u plus v, the green u plus v equals the red v plus u. So this is a true statement, just geometrically. Okay, so when you draw both u plus v and v plus u, this is called the parallelogram law. The parallelogram law is drawing the entire parallelogram that I have both in green and red to sketch the vector u plus v or v plus u. Okay, when you use just half of that, the triangle, which is all that's really required to draw u plus v or v plus u, you have what's called the triangle law. Okay, so here's an example. Here's an example. Sketch the vector, let's say a plus b. And the vector a is this arrow. The vector b is this arrow. There we are. Oops, I'm using capital there, and that's not good. You could use capitals, but we generally don't. B is that vector. Draw the vector a plus b. Well, we're supposed to use the triangle law to do this. To draw a plus b, I should do the same thing as I did with u plus v. I take the vector u and draw it, and then I take the vector v, so that the tail of the second vector v is at the tip of the vector u, and then I draw the resultant from the tail of u to the tip of v. If you didn't get that, you might want to pause, take the video back 20 seconds ago and replay it. Okay, so, but I'll be sort of replaying it in this example. To get a plus b, I need to reposition v. Well, am I allowed to do that? Yes. Why am I allowed to reposition v? Because the definition of a vector has nothing to do with its location in space. So I'm going to take the tail of b, and I'm going to move it to the tip of a. And there it is. I've moved the vector b so that the tail of b is at the tip of a. Move the description of a over here. Here's a. Here's b. So how do I get the resultant? To get the resultant vector, you draw the vector from the tail of the original vector, the vector on the left of a plus b, to the final vector b. That little red vector, that is a plus b. Okay. So let's head toward one of our first definitions of multiplication. And you might be thinking, God, we just barely talked about addition. How can you talk about multiplication? Well, this is a good time for it. Let me show you why. What should 2a, 2 times the vector a, mean? What should it mean? So, from what I have told you so far about vectors, I want to think about it this way. Is it possible for us to talk about the vector 2 as a scalar multiplied by a as a vector? The answer is no. There's no such definition of this. So the definition of 2a right now has absolutely no meaning. There's no meaning to it, just based on what I've talked about in the last 10, 15, 20 minutes. Okay. Now from algebra, we have something nice. From algebra, we know that x, that's not a vector, it's a scalar x, plus another vector is 2x. That's true. That's true. We would like the same thing to hold true for vectors. We would like the same thing to hold for vectors. So the definition, this is how we're defining 2a. Definition. This is not a result of anything. This is how I'm defining 2a. A plus a equals 2a. So let me ask you, why is that true? And if you're thinking about responding, and you respond with anything other than that, it's true because that's the definition. If you respond with anything else, you're wrong. There's no reason why a plus a should equal 2a other than the word just before it. That's how I'm defining it to be true. I'm playing God with vectors. I'm saying this is what a plus a means. It means, I'm sorry, this is what 2a means. It means a plus a. So now we have an idea, we can have an idea of just exactly what multiplying a scalar by a vector means, because we know how to add two vectors, even if those vectors are the same vector. Here's a. Here's a vector a. How do I add two vectors together? I take the second vector and place its tail at the tip of the first. So the second vector is another a. So here's another copy of a. So how do I draw a plus a? Well, if a were this vector and a were this vector, it doesn't make any sense. But if a was the first vector I just drew and a is the second vector I drew, then a plus a by the triangle law would look like this. This is silly because the two vectors I've drawn for a aren't equal. But use this idea. Well, a plus a, I take the second vector, put it as tail at the first, the tail of the tip, I'm messing up tip and tail. I take the second vector, which is also a, and put its tail at the tip of the first vector, which is also a. Then I draw the resultant vector from the tail of the first to the tip of the second. So I'm using the triangle law here. Oops. A plus a. I'm using the triangle law here to draw the vector a plus a. Okay. But that a plus a, I'm defining as equaling 2a. Now, what can you tell me about what can you tell me about the vector a plus a? A plus a. First of all, is a plus a scalar or a vector? It's a vector. It's another arrow. It is a vector. So it must have two things associated with it, magnitude and the direction. The magnitude is twice the magnitude of a, the magnitude of a, same vector a, the direction is the same direction. Direction as the vector a. Okay, so what does all this mean? 2a, which is a plus a, 2a is a vector with twice the magnitude as a, twice the magnitude of A with the same direction, as the vector A. So that's what the definition of 2A is. That's what the 2 as a coefficient of A does. It stretches the vector A out. It stretches the vector of A out. So this vector, this 2, stretches the vector A out. Stretches the length of A while preserving what? While preserving what? While preserving the direction of A. So multiplying a vector by a scalar affects the magnitude of the vector, but does not affect the direction of the vector. Okay? Okay, well, let's move on. What about negative 2A? How do I want to describe negative 2A? How do I want to describe negative 2A? In order to do that, we have to go back a little bit further. In order to describe negative 2A, we need to first consider not the negative 2 as a coefficient. We need to consider this. This is not read as negative V, although we all say it. Oops. Although we all say it. Okay. It's not read as negative V. It's read as the opposite of V. Okay. But if you say negative V, it's not gonna be the end of the world. Okay. Well, what is the opposite of a scalar from algebra? How do we define the opposite of something in algebra? You probably haven't thought of this in years. We use algebraic operations. We don't think about them. We don't think about their origins and how they're defined and stuff. We just sort of know them at this point. They're ingrained. From algebra, x plus the opposite of x, this is how the opposite of a number is defined, is equal to 0. The opposite of a number is defined this way. This is the definition of, if you will, negative x, or the opposite of x. So we want the same thing to hold true for vectors. We want v plus the opposite of v to equal, now I'm going to make a mistake on purpose, 0. This mistake is expensive on a test. It's extremely expensive to do this on a test, this mistake I just wrote just a second ago. We want something like this to hold true, but what's wrong with the equation? When you add two vectors together, do you get a scalar or a vector? The answer is you get a vector. So to write 0 makes no sense. So we know that we would like the opposite of v to be such that v plus the opposite of v is equal to the 0 vector. Okay, well, we kind of have to define what the 0 vector is. We can't do this yet because we don't have a definition of the 0 vector. So we had better define the 0 vector. Okay, it may not be obvious. It's a vector. First of all, the 0 vector is a vector. What would we like the magnitude of the 0 vector to be? 0. And here's the surprising part. What would we like the direction of the 0 vector to be? Direction. It's the only vector that has any direction you want it to be. It's the only vector that doesn't have a defined direction associated with it is the 0 vector. Okay, so back to, we want v plus the opposite of v to be the zero vector. All we have is the triangle rule for adding vectors. A, B, vectors, A plus B. That is all we get, folks. That's all we have to go on right now. Well, so let's draw V. Here's V. Now, how do we add two vectors? There's the first vector. The second vector is the opposite of V. How do we add two vectors? Well, we take the second vector, the opposite of V, and we place it so that its tail is at the tip of the first vector. Well, there it is. I've drawn the tail. Now, I would like V plus the opposite of V to be the zero vector. So I can't draw the opposite of V this way, because if I do, this will be the vector V plus the opposite of V by the triangle rule. And that resultant vector doesn't have a zero length. So I'm going to need to change the opposite of the direction for the opposite of V. Here's V. I'm going to need to place the opposite of V so it points in the opposite direction of V, so that when I draw the resultant vector, I can't draw the resultant vector. It will have no magnitude. I can't draw the vector. It's a dot. So we get that V plus the opposite of V is the zero vector. So what's the definition of the opposite of V? The opposite of V is a vector. Vectors have two things. the magnitude, sorry. What's the magnitude? How are we going to define the magnitude of the opposite of V? Same as the magnitude. Same as the magnitude of V. Look at my drawing. V and the opposite of V, they're only pointing in the opposite direction. If we're talking about going on the 605, if V was 60 miles per hour going south, then the opposite of V will be 60 miles per hour going north. The arrows will be exactly the same length, just opposite direction, and that brings us to direction. Magnitude, the direction, opposite direction. The opposite direction as A. Opposite as A? Opposite direction of A. And I think it's of. We'll make that as into an of A. Yeah. Okay. Alrighty. So we still have to worry about, what about negative 2A? What about negative 2A? Well, we're going to do something we'd like to have happen similarly. We have something from geometry, from algebra, that happens nicely. And we'd like that same thing to happen with negative 2A. So from algebra, negative x plus negative x is negative 2x. We know this. We know this. It's part of our fiber right now is science majors. We know this. So the definition, we would like negative 2A to be the vector negative A plus negative A. Why? Because we want it to happen. And there's no other reason than we want it to happen. So now Now that we have the definition of negative 2a, what should it look like geometrically? All right, well, here's a. Here's a. Then we just defined the opposite of a. We just defined it a few minutes ago. Here's the opposite of a. So how do I draw the sum of two vectors, the opposite of a plus the opposite of a? You take the second vector, and since this might be a little confusing, which one is the first, which one is the second? I'll change the second one into green. We take the second vector, and we take its tail, its tail, and put it at the tip of the first vector. So here's the second vector. Tail of the second and tip of the first. How do we draw the resultant vector? The resultant vector we draw from the tail of the first vector. Oops, I'm going to go crooked on there. From the tail of the first vector, and I went crooked again. We draw from the tail of the first vector to the tip of the second vector. All of this is so we can have negative 2a, the definition for negative 2a. You see what I mean? If you haven't had vectors, this concept of vectors, a lot of the algebra of the vectors coincides with the algebra of real numbers, but not everything. Okay. In fact, this discussion is going to break down when we start looking at the different types of multiplication of vectors and stuff. It's hard to find a comparison to the algebra of scalars and stuff for multiplication. Okay, we'll cross that bridge when we get there. So what is 2a, negative 2a? It is a vector. First of all, it's a vector. And vectors have two things associated with them, magnitude and direction. Magnitude. 2. The magnitude is twice the magnitude of a. 2 of a. Okay, that's important. The direction opposite of a. Okay, so that's how we're going to define our first type of multiplication. Remember, we have three types of multiplication. There are three types of multiplication. We're talking about the first type. It's called scalar multiplication. Of a vector. Scalar multiplication of a vector. Okay, so let's do that. Let's get really formal with this. Oops, I don't need to be in red right now. Let's let C be a scalar. And remember, a scalar is nothing more than a real number. Let V be a vector. So, CV, that's what we mean by scalar multiplication of a vector. What is it? How do we describe it? We need three things. You might think, oh, I thought we only needed two things for vectors. No, we need three things. Scalar multiple of a vector. First, is it a vector or a scalar? It's a vector. There's the first thing. If you're thinking, oh, that's obvious, no, it's not. The other two types of multiplication, one of them is going to give us a scalar as a result, one of them is going to give us a vector. So we have to be real precise here with our definitions. So CV, a scalar multiple of a vector, is a vector with length, what should the length of CV be? Well, what did the multiple -2 do to the vector? -2 made the result twice twice the magnitude of A. What did +2 do? What did +2 do? +2 stretched the vector into a vector of length twice the length of A. So both 2 and -2 have the same effect on the length of the resulting vector. So C times V is a vector of length C times the length of V, the vector V. And I've made a mistake on purpose. So think about it for a second. I've made an important mistake. What about -2V or -2A? Makes no difference. If this is correct, what I just wrote, then the length of -2V is going to be -2 times the length of V. Length is not negative. Length is not a negative quantity, ever. Length is non-negative. So there's a bit of a mistake here, and I'm going to get rid of that mistake if my surface will allow me to do it. Okay. So the length of the vector CV is not C times the length of the vector V, it's the absolute value of C times the length of V. Okay. What about the direction? And direction, what did 2 as a multiple of the vector A do to the direction? Nothing. Multiplying A by 2, 2A gives the same direction. What did -2 do to the direction of A? Almost nothing. So if I multiply by 2, the resulting vector 2A will have the same direction as A. If I multiply by -2, the direction of the result, -2A, will be the opposite of A. So C times V is a vector with length, absolute value of C times the length of V, and direction depending on whether C is greater than 0 or C is less than 0. Okay. If C is greater than 0, C times V will have the same direction as V. If C is negative, C is less than 0, C times V will have the opposite direction. So there's a real nice way to summarize all this. Suppose this is the vector W. Let's make it steeper. Easier for me to mess with vectors if I draw them a little steeper. Just a little steeper. Here's a vector W. What will 2W look like? Here, just for reference, I'm going to put a little dotted line here. 2W, well, no, we already did 2W. What will, 1.5 WB look like? It will look like they have the same direction. It'll have the same direction. Oops, 3/2. Same direction as W. Oh my goodness, my writing is getting really bad here. 1.5 W will have the same direction as W, and the length of the vector will be 1.5 times the length of W. So it stretches the vector W by a factor of 1.5. What will negative 0.5 W look like? What will negative 0.5 W look like? It will look like this vector, negative 0.5 W. It'll have half the magnitude, the length of, let me just write it out. The length of negative 0.5 w will be half the length of w, is the absolute value of 0.5, negative 0.5 rather, times the length of w. Okay, so it'll be half as long as w, but pointing in the opposite direction. Okay, so I think you get the idea. Okay. Be careful with the arrows with vectors. So, arrows to designate vectors. What is 0v? What is 0v? What is 0v equal to? 0? No. A scalar multiple of a vector is a vector. So 0v is the 0 vector. What is the 0 vector times v? What is the 0 vector times v? You slow way down before you jump to the answers with these things. Especially if you're new with this vector concept. Is undefined. There's no such thing. There's no such thing. I've never put two vectors next to each other like that. There's no such thing in our course. In advanced courses in vectors, there are such things. They're called tensors, but don't worry about that now. So, what is the opposite of v? True or false? True or false? The opposite of v equals negative 1 times v. Be careful. I've never given anything to indicate that this is not a definition. There's no definition that says this is true. So is it true or false? Well, all we have is on the left-hand side the definition of the opposite of v. If v goes like this, then the opposite of v is this vector. We talked about it earlier. It's a vector with the same magnitude of v, but the opposite direction. So what about negative 1 times v? Negative 1 times v is a vector with length, absolute value of 1 times the length of v. And the opposite of, it points in the opposite direction of v because the scalar is negative. So this is true. If you didn't understand that explanation, pause video, take it back 10, 15, 20 seconds, and listen to what I said again. I'll say it one more time. The definition, look on the right. Negative 1 times v. Negative 1 times v. From what I said about scalar multiple of a vector, c times v, it's a vector with length absolute value of c times length of v. So this is a vector. It's a vector. The length is absolute value of negative 1 times the length of the vector v. And since the scalar is negative, it points in the opposite direction. So negative 1 times v looks like this. It has length 1 times the length of v, and points in the opposite direction of v because the scalar is negative. Those two vectors, the opposite of v and negative 1 times v, are the same, so it's true. I know this is painfully slow for people who've had physics. I mentioned that before, and even if you haven't had physics, this may seem intensely detail-oriented, but it's absolutely correct that we get these details. Students don't do real well. Students don't do real well generally on the part of exam 1 that has to do with keeping track of vectors versus scalars and stuff. So we have to go really slowly with this. Okay, we'll get it. So before we get into the algebra of vectors, and there's a really nice algebra of vectors that is designed to make sense to us. Before we get to that, let's talk about the geometry of one more quantity. We've looked at addition of vectors. We've looked at scalar multiplication of vectors. What we haven't looked at is the difference of two vectors. How do we subtract vectors? So here's a definition. Here's the definition of subtraction. Definition. There's nothing preceding this. This is just how we're defining to do this. How we're defining this to be. It has its roots in what we do in algebra, but u minus v is the same thing as u plus the opposite of v. That's how we actually define subtraction in algebra with real numbers. Okay. So what about the geometry of u minus v? We already know what the geometry of u plus v is. Let's look at the geometry of u minus v. So here's the vector u. Here's the vector v. Let me draw a little better vector v than that. Here's the vector v. That's a little better. Here's u. Here's v. So I want to graph the resultant vector of u plus the opposite of v. So I'm going to draw the opposite of v. So there's v. So in green, we're looking at the opposite of v. The vector with the same magnitude of v, but opposite direction. So how do we draw u plus the opposite of v? The resultant will be from the tail of the original vector u to the tip of the second vector, negative v. So this is u plus the opposite of v, or u minus v. Now, it looks kind of odd. It looks like there's no rhyme or reason to that difference, but there is a rhyme or reason to it. What I'd like to do is move the vector v so the vectors u and v are tail to tail. I'm going to move a copy of the vector v so the vectors u and v are tail to tail. Okay. Doesn't quite look like v, does it? Looks like I tilted it a little bit. So let me redo it. That's better. Still looks a little tilted. So here's v again. I've just moved a copy of it. Remember, I can do that because why can I move copies of vectors without affecting them? Because vectors are not defined by their location in space. Now I want to move that resultant vector. I have u minus v upward. I'm going to translate it upward to its new position in red. That's the vector u minus v, which still may seem like there's no rhyme or reason to this. I want to give you a better idea of what u minus v looks like in the scheme of things by graphing u plus v and u minus v on the same graph. So here's a vector u. Here's a vector v. Here's the vector. Oops, I'm a little ahead of myself. Here's the vector u plus v. U plus v. If this is u and this is v. Now I'm going to do the same thing I did a few minutes earlier. I'm going to move v over so that u and v are now tail to tail. I'm going to translate u up so that I have that parallelogram rule that we were talking about. So there are u and v, two copies of u, two copies of v, forming a parallelogram. U plus v then is drawn from the tail of u to the tip of v. And here's the neat thing. U minus v is drawn from the tip of v to the tip of u. u plus v and u minus v are nothing more than the arrows that represent diagonals of this parallelogram formed by u and v. Okay. This is the way I remember u plus v and u minus v. Okay. So if I had, suppose I want to draw the vector, here's a good one. This is off the top of my head, so I hope this works out nice. Sketch, making this up here. Sketch A minus b and a plus b. Okay, if a is this vector and b is this vector. Okay, the very first thing I'm going to do to sketch a plus b is to draw the vectors so that the tail of b is at the tip of a. That's how we start this. Here's the vector b, a and b redrawn. Then I'm going to draw a parallelogram with the same two vectors, just moving them around. Then a plus b will appear in red. That's a plus b. And a minus b will appear in green. A minus b appears in green. So was this a good example? Maybe not the best. Sort of repeats what I did just earlier, but I'll let you be the judge. Okay, so now let's move on to the algebra, the symbolic algebra of vectors. So we need to introduce algebraic quantities to these vectors, to the concepts of vectors. So let's do that. Let's talk about what are called components of a vector. Components of a vector. So what I'm going to do is, in 2 space, I'm going to draw a vector. Okay. Suppose I draw a vector by starting in quadrant 1 and moving at a particular point and moving 2 units to the right and 1 unit up. And that's my vector. The vector is formed by drawing. Notice I get the vector by going 2 units to the right and 1 unit up. Okay, and I call this the vector A. That vector A can be drawn there, or there, or there, there. All of these are just this. They're the same. There's the same vector A drawn in different positions. You can draw one where its tail is on the x-axis. Okay. We can designate this vector A in a really convenient way. We can write A in terms of what are called components. In a similar way, we write ordered pairs to designate points. The vector A can be drawn using bracket notation 2, 1. Okay. Caution. 2, 1 is not the same thing as the ordered pair 2, 1. Why? 2, 1 is a vector. I've drawn that vector 6 times in the xy plane for you, and just to the left. 2, 1 ordered pair, that's a point. They are not the same thing. Points are locations, and vectors have no location. They're, in some sense, the opposites of one another. They do not correspond. How can we make the point 2, 1 and the vector 2, 1 coincide? You have the answer to that question. How could I make the vector bracket 2, 1 equal to the point order pair 2, 1 somehow, in some sense? The answer is I could draw the vector A as what kind of a vector? See if you remember. If you draw A as a position vector, 1, 2, 1, then you get close to having equality of the two items, but even here you don't have the same thing. The point 2, 1 is a dot. Even as a position vector, the vector A, whose components are 2 and 1, it's a vector, it's an arrow. Arrows do not equal dots. Arrows do not equal dots. Okay, so here's an example. Let's get to something. Let's do something in 3 space here. Sketch the vector B equals 1, the vector whose components are 1, 2, and 3. 1, 2, and 3 are the components, not coordinates, but components of the vector. Okay. So generally in 3 space, if you have a vector whose components are A1, A2, and A3, where the A's, A1, A2, and A3 are scalars, then if you draw the vector A as a position vector, which is kind of convenient for us here, then you imagine going from the origin A units, if A1 units, if A1 is positive, and move A2 units if A2 is positive along the y-axis, and then move A3 units in the z direction, and then draw, if you're considering A as a position vector, then you can draw the vector A with its tail at the origin and its tip at where the z value A3 would get us. Okay. Then in green, that tip of that position vector is the point A1, comma A2, comma A3. The red vector and the green dot are not the same thing. They're not the same thing. Okay, so if I want to sketch 1, 2, 3 as a position vector, I'll include that in my directions as a position vector. Then draw a copy of the axes, x, y, z, x previous, y and z. Okay, and then 1, 1, 2, 1, 2, 3. Doing the same thing I did for the general position vector A1, A2, A3. In fact, I'm including even a little more. I'm including a box here to help us really see this. So in red, here's the vector 1, 2, 3 as a position vector. B, I guess. Okay, so it's similar. If you draw vectors as position vectors, it's very similar to drawing points. The big difference is vectors are not points. They're arrows. Vectors are arrows. Points are dots. Vectors are arrows. How about a formula or formulas for displacement vectors? How about formulas for displacement vectors? Well, let's do this in 2 space first. Yeah. neaten up my axes here. Let's do this in 2 space. Suppose I have a vector in 2 space. There's a vector in 2 space. I don't know why I didn't use arrows before, straight arrows before here. Okay. Suppose this is the displacement vector from the point A, x1, y1 to B, x2, y2. And suppose I want a formula for the vector AB, the displacement vector AB. Well, not difficult to do. Not at all difficult to do. Very similar kind of algebra that you did in pre-calc and calc 2 when you talked about slopes and distance formulas. If you project the x-coordinates of the 2 points down onto the x-axis, you notice that the horizontal displacement is x2 minus x1, and similarly, the vertical displacement is y2 minus y1. y2 minus y1. So it's right in front of us. The displacement vector from A to B then is nothing more than a vector whose components are x2 minus x1 and y2 minus y1. So this is the beauty of vectors, is that they really just draw on the algebra that we already have available to us. So in R3 we would have third coordinates. So in R3 the displacement vector would just have a third difference, x2 minus x1, y2 minus y1, and z2 minus z1. Oops, if we tack on the additional coordinates, z1 and z2. Okay, this is very, very simple, the concept of a displacement vector. So, example, find the displacement vector from A, -1, 3, 4, to B, 1, 7, 6. It's probably one of the easiest problems you'll see this semester. It's simple, simple, simple. So the displacement vector AB is nothing more than a vector whose components are the x component of the second vector minus the exponent of the first vector, the second component of the second vector minus the second component of the first, and then the difference of the third components from second vector to first vector. 2, 4, 2. Nothing more to it than that. Okay. Now we've been talking about the vectors in terms of magnitude and direction. I'd like a symbol and a formula for the magnitude of a vector. It's not difficult. It's not at all difficult to come up with the magnitude of a vector. The magnitude of a vector is given by nothing more than the Pythagorean theorem. If you have a vector A with components A1 and A2, that A1 and A2, those are horizontal and vertical components of a vector. Those are just horizontal and vertical components of a vector. Specifically, here's the vector. Okay, we got a kind of an extra little vector floating around in there. Okay. So here's A1, here's A2. So the magnitude of that vector is nothing more than the square root of A1 squared plus A2 squared, just by the Pythagorean theorem. Now we have a special symbol for magnitude. The author of your textbook has decided not to use this symbol. I'm going to use the symbol throughout the course. I encourage you to, but I won't take off points if you don't use this notation. This notation is common. I don't know why the author of your textbook has decided not to use the notation. The magnitude of a vector is designated by two sort of absolute value bars on each side. This is the magnitude of a vector, and it's nothing more than the square root of a1 squared plus a2 squared. If we have a third component, a3 squared for R3. So if we have a third component, we add on a third term under the radical. Okay, so finding the magnitude of a vector is super simple. Now, if you decide to use the notation that your author uses, that's fine. The author uses the absolute values, and that's not, I don't think that's a good idea, but that's just my opinion. Author uses absolute value notation for magnitude. Okay, he writes absolute value, the magnitude of A as using the same symbols. I don't think it's a good idea because it confuses the absolute value with magnitude, but if you want to use the absolute value signs, you won't lose any points for it, okay? Okay, so we know how geometrically to find A plus B. How do we find A plus B component-wise? It's very simple. If A is the vector whose components are A1, A2, and A3, and B is the vector whose components have subscripted B's, B1, B2, and B3, then A plus B is nothing more than the vector whose components are A1 plus B1. This is so nice about vectors. At least we get this nice stuff happening before we get into the more complicated vector multiplications. B2, A3 plus B. We have some really intense stuff coming up, but it's real nice to have something not so intense. If this were subtraction, if there was A minus B, we would subtract the components in the same order. Okay. Also, stretching or shrinking or reflecting vectors is obtained by multiplying the components by the scalar CA2 CA3. That's really nice. It's really cool. Okay, so if A equals the vector whose components are -3 and 1, and B is the vector whose components are 5 and -2, then A plus B is nothing more than the vector whose components are -3 plus 5 and 1 plus -2, or 2 and -1. And let's say 7b is nothing more than the vector whose components are 7 times 5, and 7 times -2, or the vector whose components are 35 and -14. It's that simple. It's that simple. Now, I'm going to refer you to an important page in your textbook, Properties of Vectors. Properties of vectors on page, in the 8th edition, 842. Okay, and that on that page, your author summarizes the properties that we've learned and introduces a couple of other ones, including the distributive properties and so forth. Be careful as you look at these that you don't associate the properties too closely with the properties of real numbers. Although they look very, very similar, there's different stuff going on. Here's an example. I'm bringing up one property here, and then let's see the real popular one. Hang on a sec. Let's see. Oh, here. CDA is the same thing as C times DA, where C and D are scalars and A is a vector. This is one of the properties. I think it's the 7th property listed. This is not as simple a quantity as an identity that you might think. Let me ask you a question. On the right-hand side, how many different types of operations are there? How many different operations are there? One. There's only one operation on this side, scalar multiplication. Scalar multiplication. Multiplication of vectors. To convince you of that, look inside the parentheses. dA is a scalar multiple of a vector. The scalar multiple of a vector, dA, produces a vector. So ultimately, it's C times dA, which is a vector. So it's another scalar multiplication of a vector. So this is a scalar multiplication of a vector twice. Now, let me ask you the corresponding question on the left-hand side. How many different operations are there? 2. Inside the parentheses, that's scalar multiplication of scalars. And then when you do that multiplication, you produce C times D to produce another scalar, and then multiply it by the vector A. Then you have scalar multiplication of a vector. So there are 2 operations on this side. There's scalar multiplication of scalars, and there's scalar multiplication of vectors. Multiplication of vectors. So these identities on that properties page some of the identities are really hiding what's going on sort of behind the scenes, okay? They look nice. They look nice because they sort of correspond to what we're used to in algebra. But they're not quite the same thing. In fact, they're not the same thing at all. Okay, we're almost done here. We have a couple of things left to talk about. One of them is much more intense than the other. There's another way of designating vectors besides giving them in bracket and component form. Okay, there's something called standard basis vectors. Standard basis vectors. And they look like this. Small I with little hat on top, small j with little hat on top, and small k with little hat on top. Okay. These are what are called standard basis vectors. And you notice that I've made an exception to the notation here. Those aren't arrows above those vectors, they're hats. They're hats to emphasize that these vectors have length 1. These are unit vectors. These are unit vectors. They have length 1. Length 1. Now what I'd like to do is to consider the vector, let's say 2, 3. 2, 3. And I'm going to consider this vector as a position vector. Consider this vector as a position vector. And the position vectors are drawn with their tail at the origin. So let's consider the point 2, 3 as a position vector. Okay. So there's 1, 2 along the x-axis, 1, 2, 3 along the y-axis. So here's the vector. Here's the vector 2, 3. Close enough. Okay. Now here are the standard basis vectors drawn for us. I haven't defined them yet other than their unit vectors. Now here are the standard basis vectors in red. Standard basis I hat is this vector in red. This is I hat. J is this vector in red. J hat. I is the vector whose components are 1 and 0, and J is the vector whose components are 0 and 1. If I use these, if I consider the vectors in 2 space. Now, notice that the vector 2, 3, can be written as 2 times the vector 1, 0 plus 3 times the vector 0, 1. 2 times I would look like I stretched out by a factor of 2. 2 times J would be J stretched out by a factor of 3. Covered this in our discussion of scalar multiple of a vector. Oh, that looks terrible. Okay, so let me redo that. 3J. So if I take 2I and add 3J, if I take 2I and add 3J, moving 3J over, then I'm going to get the vector 2, 3. So 2, 3 can also be written as the vector 2I plus 3J. In fact, we can do this with any vector in either 2 or 3 space, as long as we introduce a third standard basis vector. So any vector A, B, given component-wise, can be written as AI plus BJ, where I and J are the standard basis vectors whose components are 1, 0, and 0, 1, respectively. Okay, so similarly in R3, the vector A, B, C can be written as A times the standard basis vector I plus B times standard basis vector J plus C times the standard basis vector K, where I is the vector whose components are 1, 0, and 0, J is the vector whose components are 0, 1, and 0, and K is the vector whose components are 0, 0, and 1. And it's very, very common in physics to use, at least in early physics, to use the standard basis vectors rather than the component definition. So, example, find a plus b if a equals I minus 2j. Fix that, that looks terrible. I minus 2j and b equals 3i plus 4j plus k. We could do plus 2k. Okay. So a plus b, if we were using components in brackets, we would just add the x components, add the y components, and add the z components. The same thing holds true if we look at the vectors in terms of the standard basis vectors. I plus j, or rather a plus b is 1 plus 3i plus negative 2 plus 4j plus, there's no third component for a. Well, yeah, there is. It's 0k. So plus 2k, or 0 plus 2k. So we get 4i plus 2j plus 2k. Or, component-wise, vector whose components are 4, 2, and 2. We have the option of using either. The very last thing I want to talk about are unit vectors. Unit vectors. Examples of unit vectors we just looked at. The I, j, and k, they're standard basis vectors. They all each have length 1. Sometimes it's necessary for us to create unit vectors other than the standard basis vectors, to create unit vectors. Suppose we have a vector A, and all we want from A is its direction. Suppose we have a vector A, and the only thing we're interested from A is its direction. Okay, so here's the vector A, and all I want is its direction. So what I could do is I could multiply A by a constant so that that constant will shrink the result down to a vector with the same direction as A, but have a length of 1. Okay, so what would I do? What could I multiply A by so that the magnitude of the resulting vector will be 1 without changing the direction of A? I can multiply by 1 over the magnitude of A. If I do that, I have a unit vector. This is a unit vector. Okay. The magnitude of that vector is 1. The magnitude of the vector is 1. So if I want to create a unit vector from a given vector, a vector who has length 5 or 7 or radical 2 or whatever, all I have to do is take that vector and multiply by the reciprocal of its length. So to finish our lecture, find a unit vector. Find a unit vector in the direction. Find a unit vector in the direction of A equals I minus j plus 2k. Okay. Now, A is not a unit vector, but I want to create one. So I'm going to create it, and I'm going to call it U for unit vector, and I'm going to put a little hat over it, not an arrow. A hat is used use the hat for unit vectors. When you're creating a unit vector, don't use the arrow. This is our only exception, I guess, to the arrow rule. For unit vectors, use hat. It's a hat. So it's 1 over the length of A times A. Well, length of A is the square root of the x component squared plus the y component squared plus the z component squared times the vector A times I minus j plus 2k. Well, 2 squared is 4. 4 plus 2 more is 6. So this is nothing more than 1 over the square root of 6 times I minus j plus 2k, or 1 over the square root of 6i minus 1 over radical 6j plus 2 over radical 6k. And that vector is guaranteed to have the same length as the original vector A, but have a unit length, have the same direction as the vector A, but have length 1. Now, you've taken in a lot of information, but fortunately this ends this video segment, and I'm looking forward to talking with you again.